All right, aloha and welcome to my talk on making and breaking Mac firewalls. My name is Patrick. I work at Digita Security, where we are creating cybersecurity tools for the Mac enterprise. I'm also the creator of the Mac security website, Objective-C. So today we're going to talk about creating or making a firewall for macOS. We're then going to shift gears. We're going to put on our hacker hats and talk about then breaking or bypassing such products. So about a year ago, I decided, hey, I want to write a firewall for macOS. So this section of the talk will describe that process in creating a free Mac firewall product called Lulu. So there's many reasons you might want to create or install a firewall. Some of the obvious ones are obviously to help protect your privacy. Firewalls are also good at thwarting cyber attacks. Many firewalls are able to generically detect malware that perhaps has gotten onto your system and now is trying to beacon out perhaps to talk to a command and control server. So what our firewall will do is monitor all network traffic and allow trusted traffic while detecting and blocking malicious or unauthorized traffic. Now, since we need to monitor all network connections, we are going to have to write a kernel extension. Luckily in macOS, Apple provides something called network kernel extensions, or NKEs, and they provide a way to modify or extend the network infrastructure. One type of NKE is called a socket filter, which, as its name obviously implies, can filter network traffic at the socket level, which for creating a firewall sounds perfect. So in order to filter network traffic and connections, we first have to register a socket filter. So you accomplish this by first filling out a socket filter structure. And this structure has various callbacks, which once registered will be invoked by the operating system anytime a socket action occurs. This then gives our firewall the ability to monitor, examine, and filter these socket actions. Now, once this socket filter structure has been populated, you invoke the socket filter register function. And this will, as its name implies, register or install the socket filter. Now, besides that populated structure we just discussed, this filter also takes the socket domain, type, and the protocol. So this means if you want to filter multiple socket types, for example, IPv4, IPv6, et cetera, you have to invoke this function multiple times. All right, so now let's talk about these callbacks, which, as I mentioned, once your socket filter is installed, the operating system will automatically invoke when socket actions occur, allowing your firewall to examine and either allow or block these events. So first up, we have the attach callback. As the slide mentioned, this is called anytime a socket is created. And it's called with the actual socket and also a cookie parameter, which can hold any socket-specific data. So here we allocate a chunk of memory, and then we store an action based on the PID of the process. If it's a process we're going to allow, we set it to allow. If it's a process we want to block, we set the action to block. And if it's a new process or something that we don't recognize, we set the action to ask. Next up is the connect out callback, and this will be called by the operating system anytime a socket attempts to initiate an outgoing connection. It takes that same cookie parameter, which we've set to either allow, block, or ask, the socket, and then the remote address that the socket is trying to connect to so we can examine the endpoint. Now, if we've previously set the action to allow, we just return OK from this function. This tells the operating system we're cool with this and it should be allowed. If we want to block this, we just return an error from this callback, and this will tell the operating system to block or deny the connection. Now, if the cookie has been set to ask, this means we're not sure what to do. You know, should we allow the process? Should we block it? We're just not sure. So we have to have some extra logic. So if we don't know what we should do, we're going to have to ask some other firewall components. So the first thing we do is still in the kernel, we set the thread to sleep, basically pausing the operation. We then ask our user mode firewall component, daemon, for assistance. And we pass the information that we have from the kernel to user mode via a shared queue. For example, the PID and the socket that's trying to initiate the outgoing connection. So the daemon now gets this request from the kernel, and what it does is it maps a PID to a path, and then first checks if this path exists in the rules database. If it's not found, meaning it's a brand new application or a piece of malware that's never been on the system before, what it then does is it sends another message to another firewall component that's running in the user's UI session, which will now actually display the firewall alert to the user. So the user now has to basically answer the question, should they allow this connection? And what we do is we wait until they interact with this alert. Once they've clicked either allow or block, this response is first sent back to the daemon. The daemon then updates the rule database and then propagates this response back into the kernel via an IO-kit interface. The kernel extension wakes up the thread that it had previously put asleep and then applies the action that the user specified, either allowing or blocking the connection. So basically that, at least from a conceptual point of view, is all the pieces we need to build a comprehensive kernel-level firewall for macOS. So we put this all together, we have Lulu. As I mentioned, Lulu is a free firewall for macOS. The entire source code for this product is available online, and as of today, you can download and install version 1.0. All right. Now, Black Hat is predominantly, at least in my opinion, a hacker conference. So now let's turn our attention to breaking or bypassing these firewalls. So imagine you are an attacker, or perhaps a piece of malware that's made it to a host. So you've infected a system. Unfortunately, there's a firewall installed. So what your goal is, pretty simple. It's to connect out to either a command and control server for tasking, or perhaps to exfiltrate some data without being blocked by whatever firewall is installed on that system. So in this part of the talk, we're first going to look at some malware, firewall-aware malware. We're then going to talk about some exploitable security flaws in firewall products, and then end with talking about some firewall bypasses. So it's actually very important for malware to detect if there is a firewall on the box. Because if they don't, as we can see on the slide, this might be their undoing. The firewall might detect when the malware, which was previously undetected, connects out, and thus alert the user that there is something suspicious on their box. Now, I've yet to see any public Mac malware that is proactively trying to bypass firewall products, but there are some Mac malware specimens that are firewall aware. What I mean by this is they actively look to see if any firewall product is installed on the system, and if there is, they will not persistently infect that box. So one example is Devil Robber. Here is a snippet of code from one of its scripts, its install scripts, and we can see what it's doing is it's checking for the presence of Little Snitch, which is a popular third-party firewall. If it finds that extension, instead of infecting the system persistently, it just executes a benign version of the application it infected and then exits. So the author of this malware basically said, hey, I don't want to be detected, so if there's a firewall, I'm just going to bail. All right, so now on to some real issues. Firewalls are obviously rather complex pieces of software. They run with elevated privileges in root or in the kernel, and unfortunately, they're often not as well written as the operating system nor as audited. So they make great targets for looking for local privilege escalation vulnerabilities. So a while back, I found a kernel bug in the Little Snitch firewall driver. Basically, it took a 64-bit value from user mode and passed this value to an allocation routine and then a copy routine. Now, the issue was the allocation routine expected a 32-bit value. So it truncated the 64-bit value. The copy, however, used the full 64-bit value, meaning we could cause a controllable mismatch between the allocation and the copy routine, giving us an exploitable heap overflow in the kernel. Another issue I found also in Little Snitch when I was working on these slides affects its installer or updater component. Basically, it would not validate that the new firewall components it was installing had not been tampered. So what a local unprivileged attacker could do is modify these components, and then the privileged firewall installer would naively use these infected or modified components and execute them as root, basically giving, again, a local unprivileged attacker root privileges. All right, so now let's talk about bypassing these products. First, we'll look at ways to bypass various products, so some specific product specific bypasses. And then we'll talk about some more powerful capabilities that can bypass all third-party firewalls. Again, the goal is to access the network without being blocked by an installed firewall. Now, I do want to make one point, and that is any security tool that is proactively or specifically targeted will be bypassable. So in my opinion, these aren't necessarily security flaws, like these shouldn't be assigned CVEs. I think that's kind of lame. However, they are very important for attackers or malware, which might otherwise be detected or blocked. So first up, we have radio silence. Radio silence is a popular firewall for macOS. And by default, it actually allows any new process. So it basically takes a more blacklisting approach, expecting the user to blacklist a process. Now, if you look at the disassembly for its blacklisting logic in the kernel, we can see it's checking the name of a process. And if the process named is launchd, it cannot be blacklisted nor blocked. So to test this, we create some malware and we name it launchd. Doesn't matter where it is, just as long as its name is launchd. We manually create a rule to blacklist the malware, and then we execute the malware. And lo and behold, even though there's a rule to blacklist it, it is allowed because it matches on the name in the kernel. So this is kind of lame, but it's a full bypass. Another popular Mac firewall product is called hands-off. And it turns out we can fairly easily bypass it via synthetic or programmatically generated clicks. So say, for example, we want to execute curl. Curl is used a lot by malware to download other components, maybe a second stage implant, et cetera, et cetera. So if we execute this, the firewall will detect that curl is generating an outgoing connection, which is good. But what an attacker or piece of malware can then do is send a synthetic mouse click to that alert to programmatically click the allow button. This will allow the connection and dismiss the alert. And there's also ways to do this invisibly so that the user doesn't see the alert pop up and the mouse generate the click. Now on to Lulu. As Lulu is open source, turns out it's really not that hard to find a bypass. By default, Lulu trusts Apple signed binaries, although it has a gray list of Apple signed binaries that perhaps could be utilized by malware to perform malicious network actions, for example, curl and netcat. So the question is, can we find a Apple signed system binary that can allow us to do nefarious network actions, but that is not on the gray list? The answer is, of course, yes. Turns out you can actually use the whois utility to exfiltrate data. This was news to me. Since whois is signed by Apple proper, as we can see on the slide, when we use whois to exfiltrate data, the firewall Lulu will see the connection because it's monitoring all connections globally. But since it's signed by Apple and not on the gray list, it is allowed. Finally, we have Little Snitch, which is probably the most popular or well-known Mac security product. And it turns out it has an undeletable system rule to allow any process to talk to iCloud.com. This means any process, even malware, will be able to talk to Apple's servers. So to test this, we can create a rule to block curl, and then we can execute curl and specify a URL that exists on iCloud. And turns out, even if we have this rule to block curl, because of the endpoint has been basically whitelisted, it is allowed by Little Snitch. So a while back, I reverse engineered the iCloud protocol and set up a command and control server on iDrive, which is also an iCloud domain, of course, just for testing purposes. So once we understand the protocol, we can write a script that will exfiltrate files, for example, something called topsecret.txt, to iCloud, to the iDrive command and control server we have set up. Again, Little Snitch will see this connection, but because of the endpoint is allowed, it will allow the exfiltration to occur. All right, so those were product-specific bypasses. They're kind of neat, but they're also kind of lame. Why? Well, the attacker will first have to enumerate what exact firewall product is installed, and then use one of these product-specific exploits. That's kind of a pain in the butt. Now, much, much better would be to have a generic bypass, which would bypass any installed firewall, basically saying I'm agnostic to whatever firewall that's installed, I'm just going to generically bypass this. And these are possible because firewalls must allow some traffic on the network. For example, system protocols, system binaries, and also the user is probably going to fully allow things like browsers, giving them indiscriminate network access. So to generically bypass a system with a firewall, we're going to do two things. First, we're going to passively sniff and determine what traffic the firewall is allowing out. And then we're going to abuse either these protocols or these applications to perform nefarious network actions. So first, to determine what processes or protocols are allowed, we can use the LSOF utility, which is a built-in system utility on macOS. You can execute it without any special privileges, and it will show you what network traffic is allowed. So this is a dump from my box. We can see things like Chrome, the browser, chat applications like Slack, Signal, a bunch of Adobe crap, basically a lot of stuff. Now, some firewalls will have endpoint-specific rules, meaning that they might say, okay, Adobe is only allowed to talk to the Adobe servers. But as I mentioned, something like a browser is going to be able to talk to any remote web server on port 80 or 443. Of course, also, a lot of these applications now talk to the cloud, for example, AWS. So even if there's a rule to say, I only want Slack to talk to the AWS infrastructure, we can probably also create a CNC on AWS. Okay, so now we know what traffic and what processes are allowed or allowed to pass through the firewall. So the first generic bypass, we're actually going to indirectly exploit the trust of a process via a trusted protocol. So on macOS, DNS requests are handled by the system MDNS responder. So if a random application or a piece of malware wants to resolve a domain, this is sent locally to the system daemon. Then the system daemon is the one that actually generates the network request. So the firewall is going to see this DNS request, but it's going to be coming from a trusted system daemon, which is generating all DNS requests for the entire system. So the firewall basically has no choice but to allow it. So what we can do is we can basically build a DNS-based CNC mechanism, which has been discussed before. And again, since the firewall is going to trust DNS requests from the trusted Apple system daemon, this will allow us to have a full command and control mechanism, which can generically bypass all third-party firewalls. Next up, let's abuse browsers. The simple fact is, if you have a browser installed, even if you also have a firewall installed, you're going to give the browser generally indiscriminate access. Because, I mean, think about it. It browses through hundreds of websites every day. There's no way you're just going to sit and whitelist all of them. And of course, this is something that we can passively determine via LSOF. We can, for example, watch for a few hours, even a few days, and build a profile of what traffic the browser allows. And then basically say, okay, it looks like Chrome is allowed to talk to any network endpoint. So the first way we can abuse a browser to do some malicious network activity based on our behalf is via AppleScript. So on the slide, there's a few little AppleScript commands. We're basically asking Safari to invisibly browse to a remote attacker-controlled command and control server. Again, the firewall will see this request, but will allow it because it's coming from the context of the user's browser. An even better way to generically bypass all firewalls is to abuse the browser's command line interfaces. All the major browsers now support synthetic browsing via the command line. Really doesn't get easier than this. So again, the firewall will see these connections, but will allow them as it really just appears like it's the user's default browser browsing to some endpoint, which is what browsers do. Yet another way to abuse any application or trusted binary is to inject a dynamic library into it. Once the library or your code is in the process context of this trusted process, from the firewall's point of view, whatever trust that application has will be also given to that dynamic library. So for example, if you have a chat application or a browser that's allowed to talk to any network endpoint, you can inject a dylib into that process. The firewall will also give that library full access because its checks or insight is really only at the process level. Now, there's many ways to inject dylibs into third-party applications on macOS. Fortunately, due to time constraints, we can't go through these, but I've listed them on the slide. Now, the final way to bypass firewalls involves getting malicious code running in the kernel. In short, if an attacker can get code running in ring 0, it's really game over from the firewall's point of view. First, most firewalls actually generically allow any traffic that originates from the kernel anyways. So you can just generate an outgoing network request. The firewall will see it, but again, since it's coming from the context of the kernel, it will be allowed. You could also do something like generically unhook or uninstall the socket filter firewall driver or extension. This will transparently disable the firewall. And then the attacker's code or any component in user mode can generate outgoing connections. And since the firewall has been effectively neutered, this connection will be allowed. Now, a valid question is, how do we get code running in the kernel? Recent versions of macOS require kernel extensions to be signed. So one way is just to bring a third-party driver that has a vulnerability along with you to the target. You then load that driver. It will be allowed because it's validly signed, and then you can exploit the vulnerability. So for example, we could bring the little snitch kernel extension, load it, and then exploit it. Eventually, Apple does blacklist some of these extensions, but not for a very long time, and this is obviously only if they know about the vulnerability. This is interesting because the Slingshot APT group did exactly this on Windows to bypass Microsoft's kernel code signing enforcement. Now, I talked about this attack at DEF CON 2016, and since then, Apple has sought to mitigate this by introducing a security mechanism called user-approved kernel extension loading. Basically, Apple says, okay, even if you have a third-party driver that's validly signed, if you try to load it, even if it's a legitimate driver, we are going to block it and prompt the user. Turns out it was trivial to bypass this via a synthetic click, and although Apple patched that, unfortunately, as is the case with many Apple security mechanisms, it's still completely trivial to bypass. So since the introduction of this security feature, it's been completely broken. So I'm going to give a talk at DEF CON on this if you are more interested in that. All right, so let's wrap this up. So today we talked about making firewalls, basically using a socket filter. It's really not too complicated. If you're interested in more some of the details or the source code, check out Lulu. Again, it's fully open source, lots of comments. You can build it, compile it, poke around, and hopefully it gives you a good idea exactly how you would go about building such a firewall. We then talked about breaking firewalls. Turns out, yes, they have security vulnerabilities, and unfortunately, they are pretty easy to generically bypass. Now, this doesn't mean all is lost, but it certainly makes a good case for defense in depth. In my opinion, you should have some other security tools, perhaps that are detecting dilib injections, or perhaps detecting if a browser is executed from the command line. More behavioral-based activities that might indicate a precursor to an attack. Now, a firewall, I don't think, should be monitoring all these other behavioral detections, but perhaps some other third-party utility can. Also, finally, I'm stoked to announce that I'm going to be organizing a Mac security conference called Objective by the Sea. It's going to be this November in Maui. We got a great lineup of speakers. And if you're a supporter of Objective-C, which you can be for $1, the conference is actually completely free. I could talk a lot about how awesome the speakers are. They're very awesome. But, come on. It's in Hawaii in November. So if you're interested, check out objectivebythesea.com. This is the resort it's going to be held. And again, it's going to be a lot of great talks about iOS and Mac security. All right, that's a wrap. Really want to say thank you for attending. Also want to thank the partners and friends of Objective-C, Digital Security, and Malwarebytes. And we have about 2 minutes for questions. And I'll also be around after the talk if there's some more questions you'd like to discuss. Yeah, great question. So in the Mojave betas that are coming out, how has Apple basically implemented any security features that may impact this? And that's a great question because they've actually limited what certain applications can do. So for example, you can now no longer use AppleScript to talk to another application. So you can't, for example, drive Safari via AppleScript. Unfortunately, you can still do things like various dilib attacks or execute Safari from the command line. So there's still multiple ways. But they are kind of blocking some of these attack vectors, some of the precursors to the attacks. So I think I would definitely install it when it comes out because it does increase the bar in terms of security. So that's a good thing. Any other questions?
I'm guessing this applies to the built-in firewall as well?
Oh, excellent question. So the built-in firewall is great, but the problem is it only monitors incoming connections. So any activity, for example, any malware that gets on your system that tries to connect out to a command and control server or exfiltrate data, the built-in firewall is not even looking at this traffic. And the majority of attacks affecting both the enterprise and end user and Mac users, that is going to be kind of the behavior. The malware is going to come in maybe via an email. The user is going to be tricked into downloading and running something. So the first network traffic that's actually going to be generated is this outgoing traffic. So it's good to turn on the built-in firewall, but it really doesn't buy you that much, in my opinion. And I think Apple did this because they don't want to annoy the average Mac user with pop-ups when, for example, the browser they installed tries to connect to the internet, because that would be confusing to at least a handful of Mac users. And Apple usually errs on the side of usability versus security. Awesome. All right, we are out of time. I will be here for a few more questions. Again, mahalo so much for attending my talk, and I hope to see you all in Hawaii this November.